Hi everyone. We received a lot of questions about the content during week 9, so I wanted to record a quick summary video going over some of the major topics and hopefully answer your questions. Here's an overview of the main ideas from this week and the lectures to hopefully give you a better idea of what we'll be talking about in this little video and what the general things are that we expect you to understand. Please know that I'm only going to briefly touch on these topics and it will not be an exhaustive explanation of everything that we want you to know. So please see the lectures and content posted by Dr. Kroom in order to get the full array of things that we would like you to know. Some statistics terminology that is helpful to understand. The first we have our p-value. The p-value is telling us whether an association that we are seeing between the exposure and the outcome is due to random chance or if there is truly an association between the two. So a lower p-value means that it is more likely that we are seeing a true association between exposure and outcome and that our results are not due to random chance. For example, if we have a p-value of 0.04, that means that 4% of our results are likely due to random chance. And I've included a little video for you here giving you a breakdown of the association between the size of our p-value and how strong of evidence that provides when we are determining whether we will reject or fail to reject our null hypothesis, which I'll talk about more in a moment. Related to our p-value is our significance level, which gives us a better context to interpret our p-value. So usually our alpha level or significance level, they're the same thing, will be notated with this Greek letter alpha that I've included. This is basically telling us the point at which we are confident saying whether we are able to reject our null hypothesis, so leading to there likely being an association between exposure and outcome, versus when we fail to reject it, if we do not have enough information at this point to say whether or not our results are due to random chance or if there's a true association. So if our p-value is less than our significance level, we can reject our null hypothesis because our association is likely not due to random chance. But if our p-value is greater than our significance level, we need to do some more research and analysis and maybe change up our hypothesis in our research question. So we will fail to reject the null hypothesis. And a note too that you will go into these concepts in much more depth if you take a statistics class, and there's a lot more nuance to these ideas. I'm just intending to give you a very general overview and understanding of these ideas. Next, we have confidence intervals, which are a range of values that we are confident saying that the true value of whatever we're calculating, it could be a slope, it could be a specific measurement, it could be a risk ratio. There's a whole number of things that confidence intervals apply to. But it's a range of saying we are 95% confident that the true answer, even if it's not the one that we calculated, is between these two values. And this is not the same thing as saying our results are 95% likely to fall into this range. We're talking about how confident we are that we have, from data analysis, determined the range that the value will fall in. Okay, so to put all these together, I have an example for you that I just made up. I don't know if this is true or not. But say we find that students who listen to lo-fi during exams score an average of 5 points higher than students who do not listen to lo-fi during exams. And I say here that we have a p-value less than 0.05 with a 95% confidence interval between 3.8 and 7.2. My apologies if my face cuts off some of the words on the slide. I will also be posting these slides separately for your reference. But our p-value less than 0.05, assuming we have a significance level of 0.05, tells us that our results are likely not due to random chance. And our 95% confidence interval says that we are 95% confident that the actual increase in score for students who listen to lo-fi is between 3.8 and 7.2. So that 5 that we calculated falls in between the range of our confidence interval. So in this scenario, given this information, we would reject our null hypothesis. And that would be, the null hypothesis would be that there isn't a change between the two groups. But you will talk much more about that in stats. Okay, next we have measures of impact, and I'll start by talking about attributable risk. So this is looking at how many cases of a disease that we're studying in just our exposure group can be linked back to the specific exposure that we're looking at in our study, versus if the outcome that we're looking at were to be due to a totally different cause. So it's like if I'm looking at whether my stomach hurts, my outcome, because I am hungry, that is the exposure I want to look at. It very well could be that my tummy hurts just because I have like gas cramps or something else like that. So usually our exposure, or sorry, our outcomes have a lot of different causes. So we're trying to see how many of those instances are due by one particular exposure, just in the exposure group with attributable risk. And when we're looking at the attributable risk percent or etiologic fraction, that is, instead of looking at a count that we calculated in the top half of the slide, now we're looking at a proportion. So we're using the same data, we're just using a different equation to communicate the impact that the exposure is having on our exposure group in a different format. Here's a nice little picture for you. I took this from Dr. Kroom's slides, helping visualize kind of the difference here. So the red would be how many people have tummy aches from gas cramps, and the blue would be, or another cause, and the blue would be how many people have tummy aches because they're hungry. Okay, and next we have population attributable risk, which can be kind of tricky to understand at first because they are similar concepts. But the main difference here is that population attributable risk is looking at the impact of our particular exposure we're looking at on the whole population instead of just the exposure group. So it's a bigger group of people, whether or not they have been exposed. So that includes people who were exposed and unexposed in the population attributable risk. More words in the name for more people that we're looking at. And it's the same kind of concept with our population attributable risk percent. We're just looking at the proportion instead of a count. A different way to communicate the same data that we've gathered. And here's a similar graph for you here, just showing the difference is that it's in the total population as exposed to just the exposure group. Okay, now we will shift to internal and external validity. This seems like it was a topic that tripped up a good number of people, so I wanted to dig into it a little more. Internal validity is looking at inside of the study. How well was our study done? Can we trust the results that we got to tell us what is actually happening inside of the study? Internal, inside. And we want to know if this same study with the same methods and everything else were done by a different group of people, would they also get the same results? And some factors that might decrease our internal validity include random error, which are related to p-values, bias in our study, any confounding factors. If we chose the wrong study design or data analysis, so say that we chose a case control study when a cohort study would have been a better way to look at the relationship between our exposure and our outcome. And generally just if the study was not done very well. And now external validity is looking at outside of the study. External, outside. So we are wanting to know if the results that we find in the study are also going to be true when we are looking at other populations or the total population that we took our participants in the study from. So are these results going to be useful in other contexts outside of our controlled environment that we're studying in? And can we expect people to behave the same way when they aren't being studied or provided the resources that we're providing them? Do they have access to grocery stores to eat the healthy foods that we're looking at the outcomes for? Are they able to stick to the same exercise regimen when they don't have someone holding them accountable to that? Things like that. And that is a concept that we can sum up by calling generalization. Can the results of our study be applied generally to other people? And something that's helpful to note is that if a study lacks internal validity, it's also going to lack external validity. So those are very tied, right? So ways that we can improve our generalizability or our external validity outside of the study is thinking about any confounders during data analysis to factor in other things that might be causing an association that we see or think we see between exposure and outcome. Making sure that our study population reflects the people that are outside of the study. So kind of taking a mini version of whatever population we're looking at, and making sure the study environment is similar to the real world. So will people be able to access the same kinds of things that we are providing them inside of the study? Types of bias is a big concept that you will see over and over again. And so I really want to make sure that we have a good solid understanding of our different types of bias in this section. So I made this little graphic for you here to show that information bias and selection bias are umbrella terms that include a lot of subtypes of that same kind of bias. So there's a lot of more specific ways that we can talk about the situation in which we have information bias or selection bias. So take a look at the screen here. All of these terms are discussed much more in depth in Dr. Kroom's lectures. I just wanted to give you this visual representation because it can seem like there's a lot of different terms to remember, but we're just talking specifically about these big, broad categories of information and selection bias and confounding bias, but that one didn't make much sense to me to put on this slide, but we'll get there. Okay, information bias very generally are factors that cause people to be sorted into the wrong box in our 2x2 table. I've included that on the slide for you here for your reference. But in those A, B, C, D boxes, since you can only fit into one of those boxes as a participant, information bias are things that would cause you to be put in the wrong box. And so it is also known as misclassification bias for that reason. And so some situations where we might encounter information bias are people who can't totally remember something in the past, whether or not they were exposed to something or not, how long they were exposed to something, and that's a form of recall bias. Say a blood test was done poorly. So it's not like sometimes when I take my cat to the vet, they don't do it very well. And so some of the red blood cells will get crushed, and then that can skew readings of things. So it's kind of that. So that would put you into the wrong box if you get a different test result because the test was done poorly than what's actually happening. And it is a very real thing to consider in public health if your participant is hesitant or afraid to accurately answer questions due to shame or stigma. So this can particularly be relevant when you're asking youth about drug use or sexual activity, or in different cultures, things are more taboo than others. So that is something that's really important to keep in mind, and nuances and the ways that we need to be sensitive to people and their experiences. And other things, say we don't have blinding in our study, so a researcher knows if someone is in the trial or control group, and they kind of ask leading questions anticipating a specific outcome, or they try to get different information from people depending on what group they're in. The placebo effect is also a form of information bias, and false positives and false negatives are also ways to think about it, and are examples of that. I think about COVID testing. That's a very recent thing that I'm sure we're all very familiar with. So that would also be a type of information bias. Next, we have selection bias, which can be a little bit trickier to understand. So in order for something to be selection bias, it has to influence the likelihood of someone both being included into the study and in data analysis. So on the front end and the back end, there has to be some factor or force that is making it more or less likely for someone to be in both of those. And now this has to be different between those in the case and the control groups. And so if we have something like random chance error, that's just inevitable because we're humans and we're not perfect. Random chance error is going to equally impact both the case and the control group, which is why it is not a form of selection bias. It can serve as bias depending on the extent of it, but it's not selection bias because it isn't favoring one group over the other. Everyone's equally susceptible to random chance error. Some examples of this are, say you are conducting a study or a survey on people's political views. So if someone has very strong political views, they are more likely to sign up to do the survey. So that's the front end. And they're more likely to answer in a specific way because they want to influence the outcome of the study. in the information that's being put out into the public. So that's on the back end. And one that we included in the discussion questions in week 9 is that if someone is in the control group, but they were really hoping to be able to receive the novel treatment, they might be disappointed that they are in the control group. So that's the front end, more disproportionately impacts those in the control group. And then they might be more likely to drop out of the study because they are disappointed and they're thinking, what's the point, right? Why am I doing this if I'm not getting a benefit from it? So then they're not going to be included in data analysis on the back end. So our healthy worker bias is a specific kind of bias where if you are sampling people in a workplace for specific workplace exposures or another reason, then you are disproportionately recruiting people into the study that are able to work. And therefore, they are probably going to report different results than someone who is not able to work at that place. So this disproportionately excludes disabled and chronically ill people who may not have the same access to be able to work the jobs that people who are more able-bodied and able to work those jobs would be. So that is healthy worker bias. And another thing to think about, who's being represented in our data, what are the impacts that that might have on public perceptions of different things and conclusions that we're making. And lastly, we have confounding bias, which is a huge topic that I am boiling down into a very quick one-slide example. So confounding is an unrelated factor that impacts both the exposure and the outcome. That's the specific distinguishing factor for confounders, is that they impact both the exposure and the outcome, and makes it seem like there's an association between two things when there really isn't. So a good example that I found from Oregon State is if we are going to an elementary school to see if shoe size is associated with reading level, if we take all these measurements and data from all the students in the elementary school, we would probably see that a larger shoe size is associated with a higher reading level. But when we break up the students by age and grade level, we'll see that that association we're seeing is actually from the grade level. And so that would be our confounding factor, because children in higher grades are more likely to have larger shoe sizes and reading levels because they're older, they've grown more, and they've been in school for longer, and they've done more reading. So that's an example of a confounder. Okay, that is the quick overview, hopefully quick, of week 9. Please, again, refer to Dr. Kroom's materials for a much more in-depth explanation of these things, and continue to reach out with any questions that you might have. We are here to support.